On the 20th of March, as the interstellar object designated 3I Atlas crossed the icy, invisible orbital threshold of Jupiter, its visual footprint in the constellation of Gemini decayed into a mere cluster of highly compressed pixels on our deepest optical surveys. The physical body of the comet is now rapidly receding into the dark, but the true analytical event has only just begun. NASA has abruptly thrown open the entirety of its observation archives regarding this ancient visitor, dumping thousands of gigabytes of raw telemetry, high-precision spectroscopy, and radiometric logs onto public servers. The scientific community has been handed the keys to the most comprehensive chemical and dynamical portrait of an extrasolar artifact ever compiled. Yet buried within the very first terabytes of this unredacted data dump lies an impossible thermodynamic contradiction, a glaring anomaly where the object's high-precision water spectra, bursting with an anomalously high deuterium content, directly conflict with its violently complex lateral, non-gravitational accelerations. A comet cannot physically accelerate at the recorded velocities while simultaneously maintaining the low-energy isotopic signatures found in this data. This paradox of cold outgassing producing aggressive orbital shifts violates our fundamental understanding of thermodynamic sublimation. And it is a puzzle that will be fully decoded and solved by the time we reach the bottom of this archive. The sheer volume of the newly released spectral data demands immediate dissection, starting with the anomalous deuterium to hydrogen ratio. Deuterium, a heavy isotope of hydrogen containing a neutron in its nucleus, requires specific thermal conditions to bind with oxygen and form heavy water ice. In the freezing depths of an interstellar molecular cloud, the zero-point energy of a deuterium-oxygen bond is lower than that of a standard hydrogen-oxygen bond. Because the universe intrinsically favors lower energy states in extreme cold, heavy water forms and accumulates far more readily in the deep freeze of interstellar space than it does in the warmer protoplanetary disks surrounding young stars. It is an isotopic fingerprint, much like a dense regional accent in a massive crowd, betraying exactly where and under what temperatures an object was born. The spectroscopic readouts from 3I Atlas show a deuterium to hydrogen ratio so aggressively elevated that it implies the object formed at temperatures approaching absolute zero, far away from the radiogenic warmth of any host star. However, this is where the physical chemistry begins to violently clash with the object's observed orbital mechanics. When a typical comet approaches a heat source like our Sun, its volatile ices sublimate, transitioning directly from solid to gas. This outgassing produces thrust, generating what astrophysicists call non-gravitational accelerations. Typically, this outgassing is slightly delayed by the comet's thermal inertia. As the comet rotates, the sunlit side heats up, but the maximum pressure of the sublimating gas is only reached after that specific patch of the comet's surface has rotated into the afternoon position. This phenomenon, closely related to the Yarkovsky effect, applies a lateral, highly predictable push to the comet's trajectory. Think of it like a spinning merry-go-round, where a child only pushes off the ground at one specific angle during every rotation. Eventually, the entire structure shifts off its center. The NASA data details a highly complex jet system on 3I Atlas, mapping lateral non-gravitational accelerations that are geometrically precise, pushing the object across orbital planes with shocking efficiency. But here is the critical failure in the standard model. The energy required to sublimate highly deuterated heavy water at the volumes necessary to produce this level of lateral thrust should have generated a massive thermal infrared bloom. Heavy water requires significantly more thermal kinetic energy to break its hydrogen bonds and sublimate than regular ice. Yet the archival infrared telemetry shows the comet's surface remained impossibly cold. The jets were firing. The lateral acceleration was recorded, but the required thermal exchange simply did not happen. The math governing the acceleration does not match the thermodynamic constraints of the outgassing volume, leaving us staring at a set of vectors that seem to defy the conservation of energy itself. If you find yourself reaching for explanations and coming up empty, you are not alone. Thousands of researchers are doing exactly the same thing right now, combing through this open archive. If this kind of deep dive into frontier science is what you come here for, subscribing means you never miss the moment something breaks open. What if this lateral movement is not the result of random, solar-induced sublimation, but the byproduct of something far more mechanically deliberate? This question hung in the air for merely 48 hours before the narrative was completely fractured by the entry of the Joint Search for Extraterrestrial Intelligence and the Chinese Fast Radio Telescope team. Instead of providing clarifying radiometric context to the NASA data, the release of their narrowband technosignature search results deepened the mystery into a profound, almost terrifying silence. From October of 2025 to January of 2026, the FAST array was locked onto 3I Atlas during 4 vital orbital nodes: its closest approach to Mars, its perihelion near the Sun, its closest approach to Earth, and the immediate post-encounter phase as it began its retreat. These 4 dates are precisely when an active, artificially constructed probe would logically transmit data. Perihelion provides maximum thermal and solar energy for power generation, while planetary flybys offer the optimal geometric alignments for high bandwidth burst transmissions to potential receivers, or even relay networks hidden within our own solar system. To understand the absolute magnitude of the negative result that followed, you first need to understand the staggering technical architecture of the 500-meter aperture spherical radio telescope. The FAST team utilized their 19-beam L-band receiver, a piece of astronomical hardware so sensitive it borders on the metaphysical. The L-band operates in the frequency range of 1.05 to 1.45 gigahertz. This specific slice of the electromagnetic spectrum is often called the water hole. It sits quietly between the emission line of neutral hydrogen and the hydroxyl radical, the 2 molecular components of water. Because water is the presumed universal solvent for biological life, and because this specific frequency band is remarkably free of the background static of galactic synchrotron radiation and the thermal noise of our own atmosphere, it is considered the universally agreed upon intergalactic hailing channel. Look, if you are going to shout across the dark forest of the cosmos, this is the acoustic frequency where your voice will carry the furthest with the least distortion. Pointing the 19-beam receiver at 3I Atlas was akin to aiming 19 perfectly tuned parabolic microphones at a single grain of sand, dropping in a silent room waiting for the impact. The data acquisition parameters were brutally rigorous. The team recorded with a frequency resolution of approximately 7.5 Hz and an integration time of 10 seconds. In the realm of radio astronomy, resolution is everything. A resolution of 7.5 Hz means the telescope was slicing the electromagnetic spectrum into unimaginably thin slivers, searching for an incredibly tight, artificial carrier wave. Natural astrophysical phenomena like pulsars or quasars emit broadband radiation. They are the acoustic equivalent of a roaring waterfall, smearing their energy across millions of hertz. Artificial signals, however, are highly compressed to conserve energy. They are narrowband, like the piercing single-note tone of a laser beam cutting through fog. The 10-second integration time acted as a temporal sponge, soaking up incoming photons to build a solid signal-to-noise ratio. It is exactly like leaving the shutter of a camera open for a long exposure photograph in the dark. Over time, the faint light of a distant star burns a bright image onto the sensor. But compiling this level of granular data over 19 individual beams across millions of miles of moving space generates an avalanche of raw electrical voltages that must be translated into coherent physics. The voltages captured by the fast feed horns were digitized and fed directly into the BLISS pipeline, the breakthrough listen investigation for SETI software architecture. BLISS is not merely a program. It is a computational meat grinder designed to strip away the chaos of the universe. The first hurdle BLISS had to overcome was the Doppler drift. Because 3I Atlas was hurtling through the inner solar system at dozens of kilometers per second, and because the Earth is simultaneously rotating and orbiting the Sun, any radio frequency emitted by the comet would not remain stationary on our dials. Just as the siren of an ambulance pitches upward as it approaches and drops as it speeds away, an artificial radio signal from the comet would slide across the fast frequency bands. The BLISS pipeline was calibrated to hunt for signals drifting at a rate of up to plus or minus 2 Hz per second. To achieve this, the algorithms had to perform trillions of continuous fast Fourier transforms, mathematically deconstructing the complex waveforms of incoming radiostatic into their pure constituent sine waves, and then tracking those individual waves as they slid diagonally across the time-frequency waterfalls. Imagine trying to measure the exact speed of a specific car on a highway while looking through a radar gun, but both you and the car are strapped to independent, looping roller coasters. That is roughly the computational scale of what BLISS was doing, continuously across every second of observation. Furthermore, the pipeline required a signal-to-noise ratio above 10. This means the amplitude of any candidate signal had to be 10 times louder than the baseline hiss of the cosmic microwave background and the thermal noise of the telescope's own amplifiers. If a signal did not breach this high threshold, it was immediately discarded as a statistical ghost. Through this grueling computational gauntlet, the BLISS pipeline successfully isolated more than 7 million candidate signals. 7 million times, the algorithmic tripwires were triggered by a narrow-band anomaly exhibiting a Doppler drift that mimicked an extraterrestrial transmitter. But identifying a candidate is only the crude first step in a much deeper, far more mathematically violent filtration process. Wait, it gets weirder. The true analytical bottleneck lies in differentiating an interstellar transmission from the overwhelming deluge of human-made electromagnetic pollution. Our planet is a blinding, deafening sphere of terrestrial radio frequency interference. Satellites in low Earth orbit, military radar arrays, deep space telemetry downlinks, and even poorly shielded microwave ovens bleed heavily into the L-band. To purify the dataset, the 7 million candidates were subjected to rigorous cluster analysis. The telemetry from the 19-beam receiver allowed the team to spatially filter the hits. If a signal appeared with equal intensity in multiple beams simultaneously, it could not physically be originating from the pinpoint coordinates of the comet millions of miles away. It had to be a loud, local source located somewhere on Earth or in near orbit. Cluster analysis grouped these candidates by their spatial and temporal metadata, effectively quarantining massive swaths of false positives. But radio frequency interference is insidious. Sometimes a rogue reflection off an airplane or a highly localized tropospheric bounce can trick a single beam into registering a hit. To hunt down these localized anomalies, the data was fed into a tensor decomposition framework. In data science, a tensor is simply a multi-dimensional array of numbers. In this context, the SETI researchers built a massive multi-axis mathematical cube representing time, frequency, drift rate, and spatial beam. Tensor decomposition allows analysts to slice this hyperdimensional cube and extract latent, hidden structures within the noise. It is mathematically analogous to looking at a complex, chaotic shadow cast on a wall and computationally deducing the exact three-dimensional shape of the object casting it. By decomposing the data, the algorithms could isolate the precise signatures of rotating satellite beacons and sweeping terrestrial radars, separating them from the hypothetical, clean, continuous tone of an interstellar probe. To finalize the purge, the remaining stubborn signals were processed using principal component analysis. This is a dimensionality reduction technique that identifies the axes of greatest variance within a dataset. In straightforward terms, if you have a massive crowd of people moving randomly, principal component analysis will mathematically determine the primary direction the entire crowd is subtly leaning toward. By applying this technique to the residual radio anomalies, the FAST team could mathematically map the variance of the background noise. If a candidate signal shared the same principal components as known terrestrial interference, meaning its subtle modulations and frequency jitter matched the messy, imprecise engineering of human electronics, it was eliminated. Through cluster analysis, tensor decomposition, and the brutal mathematical shears of principal component analysis, the 7 million candidates were systematically dismantled. The database was whittled down to 1,000, then 100, then 10. And then there were 0. Not a single credible artificial signal survived the filtration. Every single anomaly was conclusively mapped back to an ordinary terrestrial origin. The result was absolute, perfectly clean, negative data. Here is the question worth sitting with for a moment. Does the absence of any detectable signal prove 3I Atlas is a dead rock? Or does it tell us something more unsettling about the nature of truly advanced engineering? Drop your thinking in the comments, because the people who have read this data carefully are genuinely divided on this. While a negative result in science often simply means look harder, the parameters of the FAST observation establish boundaries that are deeply unsettling. Because of the astronomical sensitivity of the 19-beam L-band receiver, the negative result establishes an exceptionally strict upper power limit. Based on the inverse square law, which dictates that the intensity of a radio wave drops exponentially as it spreads out over distance, the FAST array is sensitive enough to detect staggeringly weak emissions. The calculations embedded in the archive show that if an omnidirectional transmitter on 3I Atlas had been broadcasting with a continuous power exceeding just 0.00286 watts, it would have breached the signal-to-noise threshold and been confidently detected. To internalize the absurdity of this metric, consider the following. A standard cheap terrestrial laser pointer operates at around 0.005 watts. A standard smartphone attempting to ping a cell tower utilizes around 0.6 watts. The FAST telescope stared at a chunk of matter hurtling through the solar system from the deep interstellar void, at distances stretching tens of millions of miles, and proved with mathematical certainty that the object was emitting less radio energy than the standby indicator light on a household television. Such perfectly clean, absolute silence feels mathematically unnatural. The cosmos is inherently noisy. Even dead rocks generate faint thermal blackbody radiation in the microwave and radio bands depending on their temperature and composition. The complete absence of localized, detectable radio frequency variance, especially from an object that was simultaneously observed by NASA outgassing violent jets of highly deuterated water, creates a chilling cognitive dissonance. What if the absence of a signal is not the result of a dead rock, but a carefully calculated strategy? Here's the thing. We must consider the temporal scale of interstellar transit. A civilization capable of launching an object that crosses the galactic expanse over billions of years operates on engineering principles that likely treat the speed of light not as a limit, but as a severe and crippling bottleneck. Why would such an intelligence rely on unshielded, easily detectable electromagnetic radiation to communicate? They may have perfectly understood the exact frequencies an emergent, primitive technological species like humanity would monitor. The waterhole of the L-band is an obvious elementary step in the evolution of planetary intelligence. Broadcasting in radio across the dark forest of the galaxy is akin to lighting a massive bonfire in hostile territory. It is an invitation to predation. By ensuring the object emits absolutely zero radio frequency leakage, maintaining a power profile beneath 0.00286 watts, the architects of this object left nothing that could betray its presence to the blunt, unsophisticated listening tools of a young civilization. Or perhaps our technological arrogance has doomed our search from the very beginning. We are pressing our ears against a far too narrow electromagnetic window. If you are communicating across billions of parsecs, standard radio waves are susceptible to interstellar dispersion, scattering by free electrons in the plasma of the interstellar medium and outright blocking by dense molecular clouds. It is entirely possible we are attempting to intercept a fiber optic transmission using a tin can and a string. An advanced probe might utilize non-electromagnetic channels that seamlessly bypass the physical clutter of the galaxy. We are ignoring the potential of high-energy neutrino beams, which can pass through entire stars without interacting with ordinary matter, providing a perfectly uncorrupted point-to-point communication medium. We are entirely blind to high-frequency gravitational waves, ripples in the very fabric of spacetime generated by microscopic engineered mass oscillators inside the probe's core. They might be utilizing dark matter coupling or quantum entanglement architectures where information is not transmitted through space at all, but simply instantly flipped between paired macroscopic states. The silence of 3I Atlas in the radio spectrum does not prove it is dead. It merely proves it is not using the primitive acoustic equivalent of smoke signals. The silence, therefore, serves as a mirror, reflecting the extreme limitations of our own analytical paradigms. But the physical data archived by NASA remains immutable, and it is here, at the intersection of the radio silence and the chemical spectroscopy, that the true nature of the anomaly begins to finally crystallize. Thousands of researchers are currently sifting through these open archives, desperately searching for hidden inconsistencies. But the answer already lies in the paradox we established at the very beginning of this data dump. Recall the impossible thermodynamic contradiction: highly deuterated water requiring high thermal energy to sublimate, combined with a violently complex lateral acceleration, resulting in zero infrared thermal bloom and, as we now know from FAST, zero localized radio frequency leakage. How does an object outgas and accelerate without generating detectable heat, or emitting even 0.00286 watts of mechanical or electromagnetic noise? The solution reveals itself when we stop looking at the jets as a random geological phenomenon and start analyzing them as highly engineered, passive structural mechanics. If the object was constructed with an internal, highly porous metamaterial lattice, a labyrinth of microscopic de Laval nozzles, it could utilize the deep cold ambient vacuum of space to its advantage. A de Laval nozzle is a specific geometric tube that pinches in the middle, used in modern rocket engines to accelerate hot, pressurized gas to supersonic speeds. However, if an artificial von Neumann probe was wrapped in a thick, ablative shield of heavy, deuterated interstellar ice, it would not need a hot engine to steer. As the object approached the sun, the barest minimum of solar radiation would cause a microscopic layer of the heavy ice to undergo phase transition. Instead of violently sublimating and expanding outward in a thermal bloom, this extremely cold, slow-moving vapor would be drawn inward, funneled through the engineered microscopic nozzles within the metamaterial lattice of the hull. By forcing the low-energy vapor through these precisely calculated geometric constrictions, the internal pressure of the gas would drop while its velocity increased exponentially. The gas would be accelerated to hypersonic speeds entirely through passive geometric mechanics, requiring absolutely no moving parts, no electronic valves, and zero internal power generation. The highly directional, high-velocity exhaust would shoot out the other side of the comet, providing the aggressive, geometrically precise, lateral non-gravitational acceleration documented by NASA's optical and telemetry arrays. Because the entire process relies on the physical geometry of the internal lattice rather than active thermal combustion, it produces zero infrared heat signature. And because the system is entirely passive, driven only by the ambient, microscopic phase shifts of the ablative ice shield, it requires zero electrical power. That elegantly explains how the FAST array could stare at a dynamically maneuvering object and detect less than 0.00286 watts of electromagnetic radiation. The data points no longer contradict each other. They align with terrifying perfection. The high deuterium content is not just an indicator of interstellar origin. It is the fuel source, chosen precisely because heavy water's unique thermal properties allow for incredibly stable, low-temperature phase transitions, ideal for passive metamaterial funneling. The non-gravitational lateral accelerations are not the result of random solar heating on a spinning rock. They are the calculated course corrections of an inert, deep space navigational system manipulating vacuum geometry to steer itself around the gravitational hazards of Jupiter and the inner solar system. And the flawless, absolute radio silence documented by the BLISS pipeline, cluster analysis, tensor decomposition, and principal component analysis is not an accident. It is the signature of a machine that operates purely on the macroscopic laws of thermodynamics and structural geometry, entirely devoid of the messy, leaking electronics of a primitive civilization. As 3I Atlas continues its silent departure, retreating beyond the orbit of Jupiter and fading into the stellar backdrop of Gemini, it leaves behind an archive that fundamentally shatters our technological hubris. The comet's silence grows louder with every gigabyte of data processed, hinting that the real story of this interstellar visitor is only just beginning. It was never about listening for a radio signal. It was about learning to read the thermodynamics of the silence itself. The key to recognizing extraterrestrial engineering has been successfully downloaded onto our public servers, waiting in the cold mathematical alignment of isotopes and orbital vectors, fundamentally changing what humanity will look for the next time the deep dark throws something toward our sun. If that idea sits with you the way it does with us, hitting the like button is the simplest way to make sure this kind of rigorous, evidence-based analysis reaches the people who need to see it.